Hello everyone! Today I'm going to present our CVPR paper titled Improving Transferable Targeted Attacks with Feature Tuning Mixup. I'll go through the following parts of our work: background, motivation, methodology, experiments, and conclusion. Let's start with the background. Adversarial examples are images that are modified by small, human imperceptible perturbations to fool DNN models. There are two main types of adversarial attacks: non-targeted and targeted. Non-targeted attacks aim to make the model misclassify an image into any incorrect label. Targeted attacks, which are more challenging, attempt to make the model classify an image as a specific target label chosen by the attacker. Our paper focuses on transferable targeted attacks. This means the adversarial examples we generate should not only fool the surrogate model used to create them, but also fool other models with different architectures performing the same task. In our setting, we assume that the surrogate model is white box, meaning the attacker has complete knowledge of it, while the target models are black box. The attacker has no access to their parameters or gradients. Here is an example. In the bottom row, the adversarial example is classified as unicycle by both the surrogate model ResNet50 and other target DNN models. This demonstrates strong transferability. As for our attack setup, we assume the attacker only has access to a white box surrogate model and does not use any extra training data. Most existing transferable attacks are based on gradient-based frameworks. Among these, input transformations and feature augmentation are two common strategies. However, current transferable targeted attacks face two main challenges: limited transferability and high computational cost. From this figure, we can see that our method achieves the best transferability while keeping low computational cost. Let's talk about our motivation. We observe that the feature augmentation-based method CFM outperforms input transformation methods in both transferability and efficiency. So we decided to work in the feature space. CFM's core idea is to disrupt the surrogate model's features to improve transferability. However, CFM applies random feature perturbations in an attack-agnostic way, without explicitly optimizing them for the attack goal. We believe this presents an opportunity for improvement. Thus, we propose a new method called Feature Tuning Mixup, which intentionally adjusts the feature perturbations during the attack, rather than applying them randomly. Here's a brief overview of our FTM. FTM first introduces learnable perturbations into the deep layers of the surrogate model. In each attack iteration, a small subset of layers is randomly selected and combined with random clean features. We compute gradients for the learnable perturbations in adversarial image using only one forward and backward pass, similar to standard attacks. We update the selected learnable perturbations in adversarial image, while unselected perturbations remain unchanged. This design allows FTM to optimize feature perturbations for the attack, reduce overfitting to the surrogate model, and significantly improve transferability. Here is the procedure of FTM. The goal of FTM is to minimize the adversarial loss while maximizing the impact of learnable perturbations. FTM has two main stages: perturbation injection and perturbation update. In the injection stage, we combine CFM with our learnable perturbations to introduce feature-level noises. The entire method is built on the MyFGSM framework. Since FTM can efficiently perturb the surrogate model, we further enhance the attack using an ensemble strategy. We create multiple perturbed copies from the same surrogate model, apply FTM to each one independently, and combine them into an ensemble. Now, for the efficiency analysis. Our FTM does not involve any complex transformations or additional forward and backward passes. This makes it theoretically efficient on both CNNs and VITs. In contrast, existing methods such as SI and VT require additional backward passes, and ODI involves computationally expensive input transformations. We strictly follow the experimental settings used in previous works. In addition, we evaluate our method on a wide range of models, including 10 CNNs and 5 VITs. Experiments show that our method outperforms existing methods by a large margin. In many target models, FTM achieves over 10% higher attack success rates compared to previous methods. We also run experiments with different surrogate models, demonstrating both the strong transferability and low computational cost of our method. To test the generality of FTM, we further evaluate it on real-world black box commercial LLMs. Here, FTM generates targeted adversarial examples on a VIT model, achieving a 40.5% average attack success rate on 4 widely used LLMs. This indicates that current multimodal LLMs are vulnerable to our attacks. Finally, let's summarize our paper. We study the challenging problem of improving transferability in targeted adversarial attacks. We demonstrate that feature-level augmentation is a promising direction for achieving high transferability with low cost. We propose Feature Tuning Mixup, which combines attack-specific feature perturbations with clean features in the feature space. To efficiently optimize the feature perturbations, we design a momentum-based stochastic update strategy. Our FTM achieves state-of-the-art adversarial transferability across various target models. Thank you for listening.